So we now know how to make ionic compounds. Metal plus a non-metal. We can do all sorts of things about combining charges, figuring out charges, naming them. It's tedious work, absolutely tedious work, but we know how to do it. But what we haven't talked about is what happens when we have a non-metal and a non-metal. So if we have a non-metal and a non-metal, like here we've got hydrogen and hydrogen, both non-metals. What do we know about hydrogen? It's just got one electron. What do those guys do? Well, is hydrogen going to give away an electron to hydrogen? No, right? Why would he give away an electron? Who would give away the electron? Who would take the electron? And so when we have a non-metal plus a non-metal, we actually don't end up doing the giving away electrons and taking electrons thing. We do what we call sharing, and sharing is caring. Right? So what do we have? We have hydrogen number 1, hydrogen number 2. Each of them has one valence electron. If you look at their nearest noble gas, it's helium, which has 2 valence electrons. And so what we find is that instead of one of them giving away an electron and the other taking an electron, they just combine with each other. They move up and they hug each other, and they share their electrons. Hydrogen orange does not give away its electron to hydrogen green, or vice versa. But if you now draw a little circle around the orange hydrogen, what does he see when he looks around him? He sees 2 electrons, and he's happy because he looks like helium. If I draw that circle around the green one, same thing. He looks around him and he sees 2 electrons, and he looks like helium, and he's happy. This sharing of a pair of electrons is called a covalent bond. In fact, it's called a single covalent bond. I'm going to put that up here in carets because we're sharing one pair of electrons. And a covalent bond is different than an ionic bond. An ionic bond, with sodium chloride, sodium gave away its electron, chloride took it, and that's how they bonded to each other. Here, they're just sharing. The orange hydrogen still has his electron for the most part, the green hydrogen the same, but they're sharing it, and they make what's called a covalent bond. Let's look at chloride. What do we know about, chlorine? What do we know about chlorine? Well, if you count up its valence electrons, it's got 7. Remember, we draw those valence electrons as dots around there, and we look at valence electrons, those outermost electrons, because that's what another molecule or atom coming up is going to see first. So we've got red chlorine there. We've got blue chlorine here. They have 7 valence electrons. How many would they like to have? 8. Octet rule. They're not going to give away and take because they're both non-metals. And who's going to win, chlorine versus chlorine? Okay. So what do? They come together, they hug, they share. And if we draw a circle around our red chlorine, he sees 2, 4, 6, 8 electrons. And if we do the same around our other one, our blue one, he'd see 8 electrons. Both chlorines are happy. They are sharing a pair of electrons, and we have a single covalent bond here. So hydrogen, chlorine, both make single covalent bonds. When we write their formulas, we just write this as H2. We write this as Cl2. But what's actually happening is those chlorines are sharing one pair of electrons. So let's move on, try to do a few more. Oxygen. What do we know about oxygen? It has 6 valence electrons. 1, 2, 3, 4, 5, 6. And purple oxygen over here has 1, 2, 3, 4, 5, 6. How many would it like to have? It would like to have 8. And in ionic compounds, it took 2 electrons from a metal in order to get 8. But it doesn't do that in a covalent. In covalent, non-metal to non-metal, it's going to share. Now, if it needs 2 more electrons, guess how many it's going to share? It's going to share 2. And so this oxygen goes over here, hugs this oxygen. And now we're not just sharing 1 pair of electrons, we're sharing 2 pairs of electrons. since they are sharing, we call that covalent bonds, but we now call it a double bond because it's two pairs of electrons that are being shared, a total of 4 electrons being shared, a double bond. You can guess what's going to happen with nitrogen coming up. I'm going to violate my own rule. What do we know? Nitrogen has 5 valence electrons. My rule was generally we don't put more than 2 electrons on one side, but I know what's coming, so I'm going to put 3 electrons on my nitrogen over there. 3 on that one. Nitrogen has 5 valence electrons. It would like to have 8. What's going to happen? They're going to hug. They're going to share 3 pairs of electrons. 1, 2, 3. And what do you think we call that? We call that a triple bond. And so nitrogen has a triple bond. We write the formula just as N2 because there's 2 nitrogens there. We don't do anything special, but we know that inside there, they're sharing 3 pairs of electrons. Now, if you imagine connecting things together, if you connect them 2 pinkies, that's like a single bond. Right? You can tear that apart if you really needed to. You put enough energy in, but you get 2 pairs. Right? That's a little bit harder to pull apart, right? But I can. Now, how about if I get 3 pairs? Right? Well, 3 pairs is going to be really hard to pull apart. And a triple bond is a lot stronger than a double bond. A double bond is a lot stronger than a single bond. Now, what about carbon? Carbon, we know, has 4 valence electrons. So can we draw this? 1, 2, 3, 4. Carbon over here. Carbon over here. 1, 2, 3, 4. We take this guy. We move them over. They hug, and we form a quadruple bond? The answer is no. It's actually just not physically possible for this to happen. You can't make a quadruple bond. And so carbon doesn't play this game. It plays a slightly different game. And we're going to see what that is next. But very simply, when we can, we just form these single bonds, double bonds, and triple bonds. So what game is carbon going to play? Well, carbon here, we says, has 4 valence electrons. And what's do first is we're going to try and get carbon to attach to hydrogen. So hydrogen comes in. He's got his 1 valence electron. He says, hey, I'll share my electron with you. And hydrogen, if you look around him, he now sees 2. He's perfectly happy. But carbon only sees 5, and he's not happy yet. So what does he do? He calls another hydrogen over and says, hey, you got another electron you can share with me? And you get something that looks like that. And so now we've got that hydrogen over there is happy, but carbon's still not happy. He only sees 6, so he pulls another hydrogen, calls him over, and we get something that looks like that. That hydrogen is happy, but carbon's not happy yet, so we pour another one. We get that one over there. Now, what does carbon see? He sees 2, 4, 6, 8, and he is a happy carbon, and we find that that's actually what carbon and hydrogen make in the real world. They make CH4. You're never going to find CH3 sitting around. You're never going to find CH5 sitting around or CH2 because that means the carbon's not happy. In order to be happy, he needed those 4 hydrogens surrounding him, so there would be 8 valence electrons. And that's how we start to make bigger and bigger and more complex molecules, is we can attach multiple things to carbon atoms and other atoms that require multiple electrons in order to be happy. So we end up with CH4 right there. So how are we going to draw these dot diagrams? Well, it turns out what we've been doing so far is drawing them like this. We've been drawing all the dots. I'm going to draw silicon dioxide here. It ends up looking something like this. And boy, that's a lot of dots to draw. And as you can imagine, as molecules get bigger and bigger and bigger and bigger, you're going to have to draw more and more and more and more dots, and it just gets really tedious. So what chemists have done is they've said, hey, look, let's define a line to mean the same thing as 2 electrons. And where we're sharing these electrons, let's use lines to mean pairing sharing of electrons. And so instead of writing all these dots in the middle, I'm just going to draw lines in the middle that look something like that. Still draw these dots over here. And you'll see some people draw things like that. Remember that line over here on the left means 2 electrons. So this one corresponds to these 2 electrons. The bottom one corresponds to the other 2 electrons. And so we still have the same number of electrons we had in the previous picture. Whenever I count a line, I always count by 2s. Electrons almost always come in pairs of 2s. So you'll see me count by 2s quite a lot. Well, if we could draw lines for those inner dots, can we draw lines for those outer dots? Absolutely. And we end up with something that looks a little more like this. I'm going to draw it all in red here. And wow, that was a whole lot easier to draw. And so that's what most chemists end up drawing, is they draw all lines where they can whenever there's pairs of electrons. This is going to be the one we're going to most commonly use in this class. Okay. Now, you will see people quite often draw this and not have those extra electrons on the outside of those oxygens. That's not a good idea in this class. When we're still learning this kind of stuff, we want to always put that there. So I'm going to put an X on that and say we're not going to do that in this class. People just do that just because it's a little quicker, and as you get good at these things, you realize that even without drawing those extra electrons on the oxygen, people generally know that they're there. So we're going to draw this for most of our structures. Every time we've got a pair of electrons, we're going to draw a line to represent it. Alrighty, so the next thing we have to do is figure out how do we name these kind of compounds. And I'm going to put those rules aside just for a second. The first thing is you have to make sure you've got a non-metal plus a non-metal. 2 things from the right-hand side of the periodic table. If you've got a metal, then you're going to use that ionic naming that we went over before. But we have 2 nonmetals. Now we can start naming things. Let's name something that you're pretty familiar with. CO2, carbon dioxide. So what did I have to do here? I used carbon, so the first element just got his name. The last element did that IDE thing again. We saw that when we were doing the ionic naming, we took the first, usually syllable of the second element and turned it into IDE. But we added this other thing here called di. Now, why did we have to say di? When we had something like calcium fluoride, we didn't have to say calcium difluoride, even though there were 2 fluorines. Why do we have to say dioxide when there's 2 oxygens? And the reason is calcium fluoride CaF doesn't exist. However, CO does exist, and it's called carbon monoxide. So the reason that we have to use these words and phrases to tell us that I've got 2 oxygens, 1 oxygen, is because all of these different compounds can exist. And we need a way to distinguish between carbon dioxide, it's what you breathe out, and carbon monoxide, it'll kill you. Very important distinction between those 2 molecules. So, what's our general rule? Well, our general rule is we're going to count each of our atoms, and we're going to use it's usually Greek notation, which for 1 is mono, 2 is di, 3 is tri, 4 is tetra, a 5-sided shape is a pentagon, 6, a 6-sided shape is a hexagon, 7, you might have seen different words for this, but we're going to use hepta, 8, octa for octagon, 9 is my favorite, nana, okay. And then 10, a decade, is 10 years, so we're going to use deca. So we're going to count our atoms like that. Now you'll notice what I didn't put when I was naming this is I didn't say monocarbon monoxide. I didn't say monocarbon dioxide. It turns out when you have 1 of the first kind, you don't have to say, and you shouldn't say, the mono. But if you had more than 1, we would, and you'll see that in just a moment. Let's name no. It's my children's favorite word sometimes. No. Well, what is that? That's nitrogen. We have 1 oxygen, and so we're going to say monoxide. Notice what I didn't write was monooxide. We often will abbreviate that in chemistry. If there's 2 vowels together, we'll often shorten it and take off one of the vowels. But if you wrote monooxide, I'd be okay with that as well, but most of us will call it monoxide. Well, it turns out N2O also exists. That's laughing gas. What are we going to call that? Well, there's two nitrogens, so 2 is di, so it's dinitrogen monoxide. Okay, other things exist. N2O4 exists. What are we going to call that? That's going to be dinitrogen. And 4 was tetra, and so it's going to be tetroxide. Again, you could write tetraoxide, but most people will write tetroxide. We could go on and on. There's a lot of those nitrogen and oxygen compounds that exist, but the point is that you have to count each one of them. And the only time you don't use a count is when the first element in your formula has only one, and then you don't use the mono. But what I always like to keep in mind is that you know the names of those two. If you can remember carbon monoxide and carbon dioxide, you've pretty much learned all the rules that you need to know, as long as you verify that you have a non-metal and a non-metal, two things from the top right of the periodic table. So let's just do one more and see how you're doing. SF6, what would that be named? Sulfur hexafluoride. SF6, sulfur hexafluoride. What's also not too difficult is to go from the formula to the name. People like this a lot better than doing it for ionic compounds. If we have a formula that says P2O5, to name it, we just count everything. We say diphosphorus. The first element always is just called by its name in ionic compounds and covalent compounds. And then do you remember what 5 is? It was penta. And again, we've got that pentaoxide, but most people will just write pentoxide. But if you write pentaoxide, that's perfectly fine by me. So diphosphorus pentoxide. So we can go from a formula to a name to a formula. Just remember to count everything as we go. Alrighty, remembering that table about the different numbers, mono, di, tri, etc. And that's how we can do that. Okay, so your turn. What's the name of N3Cl2? So take a moment to try to answer that one. What you should have noticed, these are both non-metals. And as soon as they're both non-metals, you know you're not going to use any parentheses. Right, those parentheses are only for ionic compounds. And we're just going to count things. We've got 3 nitrogens, so it should start with trinitrogen. Trinitrogen, it's going to be this one. Why not dichloronitrate? Because we had that N first. We're going to name that one first. Why not just nitrogen chloride? Because 2 nonmetals, we need to count. We need to say I've got 3 nitrogens, and 2 chlorines. Right, so that's how we make and name covalent compounds. Covalent means non-metal plus non-metal. Thanks.